my pleasure to be here to introduce and speak a little bit about our Senior Capstone projects and seniors. Tonight you'll be hearing from Solomon Gardner and Eli Lattimer, and we'll get into what they're doing in just a little bit, even though there's a little hint here and there about what they're doing. So I guess I should say who my name is Molly McKinnon. I teach humanities and English here at the high school. And I also, along with Manish Shabano there in the back, we're like the co-coordinators of the Capstone project here. So what is that? So a capstone project is a year-long independent project that seniors do here at Shining Mountain. It is not for, well, it is for high school credit, but it's not part of your class load, so it all has to happen outside of your school hours mostly. So it can be something that you're really wanting to acquire, a skill or something that you've been really yearning to learn about and be able to do or make. Or it could be something you already know how to do, but you want to take it to the next level. So a capstone comes with an ask for a mentor. And a mentor can be, mostly they're a professional in the field that you choose to do your capstone in. They can be someone local, they could be someone famous. There can be 5 mentors for different parts of your project. And these people do not do your project for you. They do not tell you when to do something or what to do. They just check in with you and make sure that you're moving along, and then you can talk to them about your progress and how that's going, and they guide you, but it's all on you. So you can imagine when you have a year where you are applying to college, you are maybe taking the SAT one more time, you are being asked to represent the high school in the rose ceremony, potentially, or all kinds of festival things in the school. You're being tested on all kinds of stuff by evil teachers. And you have your graduation speeches you have to make, and you have to graduate, and you have to do a capstone project. So it's a big, big year, and I'm sure that these two are so thrilled that it is this evening, and it'll be all over in just a short while. Yeah, and they can move on to the next thing. You can imagine that undertaking something like this could teach you some skills that have nothing to do with your project. Like, do I have enough money to pay the rent and buy the Rivendell Lego set? Or shall I take that mountain bike ride before I can get to work? Do I have enough time? So it teaches you responsibility, it teaches you time management, it teaches you task management. It's maybe, for a lot of people, it's about 85% procrastination. And then something happens, probably panic, and then they kick it in, and amazingly, they stand here with fully formed projects. And it really is amazing. So I'm not going to say anything more. At the end of the presentations, we'll open the floors of questions for both of the seniors. So I don't know, be thinking about what you want to ask them. And so Solomon is going to start us off with building an 8-bit computer, and I'm so sad that I don't have that lovely title that you gave it that you told me I couldn't use. Well, anyway, it was very poetic. And then we also have, second, Eli Lattimer, who has made his own sleeves. So, Solomon.
Hi, everyone. So I had a version of this presentation about a month ago, and I gave it to my mother, and she looked at me and she said, I have no idea what you're talking about. So I made another version of this, and I came a week ago and showed this to Eli and Miss McKinnon, and they both said, I know about 50% of what you're talking about. So I redid it, and I gave it to a bunch of middle schoolers yesterday, and they knew what I was talking about. So this is the 3rd version of this presentation, and let's just jump right in. So I built a computer. Now, when you look at this, you might not think computer. This is subtracting numbers. This is displaying information in just a much higher resolution. So what is a computer? By the Merriam-Webster definition, a computer is a programmable, usually electronic device that can store, retrieve, and process data. Now the key word here is programmable. Every computer, this computer, the computer I built, the computer I usually have in my pocket, comes with a general set of instructions. The user then tells that computer which instructions to execute and in what order. For example, read two numbers, add them together, and output the result. That same computer could then read three numbers, add the first two, subtract the third one, and then output that result. So it's not bound by specific execution of its instructions, but is rather able to execute any of its instructions at any time. Modern computers, especially electronic computers, operate in ones and zeros. And we'll get a little bit more into that later. But, okay, we know what a computer is. What is it made of? And I will be focusing on electronic computers for this presentation. I know I said usually electronic. There are mechanical computers. For example, simple calculators, old like star clocks. However, these all function very differently from each other and from the computer that I built. I didn't build a mechanical computer, and they're very, very complicated. So talk to me afterwards or do your own research. Anyway, an electronic computer is made from transistors. Again, more on this later. I will get to everything, I promise. And these are combined to form logic gates, simple addition, memory, clock circuits, and other components. A computer also contains things like capacitors to hold charge, resistors to lower or lessen that charge, and in my case, as you can tell, a lot of wires. Okay, let's move another level down. What is a transistor? At its base, a transistor is a device that uses a very small current to control the flow of a very large current. This is a photo of a MOSFET transistor, a type of, oh, it's working, great. Type of transistor that is not used in my project, but is easy to show on a screen. As you can see, it has three pins here. This is the base, the collector, and the emitter. When a current is applied to the base, a gate is opened between the collector and emitter. In this way, it functions sort of like an electronic switch. However, as we will see in a moment, arrays of these, when combined together, can start to do some very interesting things. Now, let's talk history for a moment. This man above me is Nikola Tesla. Well, he is better known for his work on alternating current, induction motors, and a little bit on the light bulb. His lab also discovered a curious property of electricity, namely that in a vacuum, when you discharge electricity, it creates a cornea around the point rather than a spark of high density voltage. This cornea can be controlled by outside voltage and allow for the creation of something called a vacuum tube, which functions very similar to an old transistor. For 40 years, vacuum tubes functioned as our diodes, allowing current to flow in one direction, TV displays, when modified to shoot electron beams at the screen, and transistors in early computers, radios, and other electronic devices. However, they would heat up quickly and burn out, needing replacement before the computer could keep working. In ENIAC, the world's first true computer, contained over 18,000 vacuum tubes. ENIAC also had an entire Army Corps on hand with boxes of vacuum tubes ready to replace ones that burnt out, which wasn't always obvious and happened about twice an hour. Calculations could often take days longer than expected because one would burn out and no one would find it. Luckily, in 1947, at Bell Labs in New Jersey, the world's first solid-state semiconductor-based transistor was created. These use a property of transition metals, namely silicon and germanium, there's a process called doping, and it allows us to change whether this material is electronically conductive or not electronically conductive by injecting or displacing electrons in that material. This is a photo or a diagram of an NPN transistor named after the types of doping used. N-type doping, followed by a layer of P-type doping, followed by a layer of N-type doping. This is a little beyond the scope of this presentation because this is actually quantum mechanics, but as best as I can describe it, the electricity is able to flow through parts of this, but not through others, and when applied voltage to that base pin, which is the p-type doping. The n-type dopings are able to connect because it fills with transistors, or electrons, and then when the electrons are removed, there is no longer space for the current to flow between the n-type doped areas. These are used in my project from here and into the integrated circuits that I'll talk about later. NPN transistors are very fast, very small, and very heat efficient. Since 1965, the number of transistors we've been able to fit on a chip of a given size has doubled every 2 years. The transistors in my laptop now are about 5 nanometers wide and contain about 11 silicon atoms. Let's drill that point home a little bit more. ENIAC, the world's first computer, cost $7 million adjusted for inflation. It weighed 27 tons, it took up 300 square feet, and it used 18,000 vacuum tubes. And as I've mentioned before, it failed almost every day due to burnt out vacuum tubes and other mechanical failures. ENIAC was so large and created so much heat, it would create its own weather systems in the building it was housed in, leading to condensation, moisture damage, and other problems. This is my laptop. This is the ROG Zephyrus G14. It costs about $2,000, which is a lot, I know, but I wanted to spend it. It weighs about 3.3 pounds. It fits in my backpack, and between the central processing unit, the graphics processing unit, and the solid state memory, it contains over 50 billion transistors. It's been running for almost a year now, and I've had no problems. So we understand what a computer is, how they're made, down to a pretty base level. So let's talk about my computer. My computer is made on something called a breadboard. Ignore this chip for now. I will talk about it later. This is nice. So if you people here compared to the amount of middle schoolers I had, you can all see this. This is incredible. A breadboard is a rapid prototyping device used in electronic circuitry that allows me to replace and form connections between these wires without soldering or gluing or any kind of permanent attachment. This allows me to build something. It doesn't work, I rebuild it, it usually still doesn't work, and I rebuild it until it can work without me having to desolder or break bonds and create a mess. And each of these breadboards is a component on my computer. I've done this so that, well, in the future, I'm going to be donating this computer to Ryan Langendorf in the back for use in educational purposes in computer science classes at this school. And I wanted it to be somewhat readable. Now in the future, I will be replacing some of these wires to make it a little bit more readable. But for now, this is what we have. Each breadboard is a component. And we're gonna go through each of the components one by one and talk about what they do and how they're built. But first, I wanna talk about some of the components on those components, namely integrated circuits. This is a half adder, and we'll talk more about half adders in a moment, but this adds a 2-digit binary number to another 2-digit binary number and outputs the result through these wires into LEDs. This cost me about $10 to make and is this big. This small piece on this piece component right here is also a half adder. It's actually double the half adder I built. It's a 4-bit half adder. It cost me about 10 cents, doesn't fail like mine does, and is much smaller. Originally, I was going to build my entire computer out of these transistors. However, my mentor, who I'll talk about in a moment, Fred Anixtein, quickly convinced me this was not going to be possible. So we built these out of these Texas Instruments 74 series low latency integrated circuit chips. Now, each of these chips has a different function, and I'm going to go through each of them in a moment. But this component here in the middle, right here, is the ALU, or Arithmetic Logic Unit. This is the core computing area of this computer. It adds numbers, subtracts numbers, multiplies numbers, and sometimes sort of can divide numbers. Division is actually very hard computationally in this scenario, but I can fake it. On each component, including this one, is a chip here that controls whether this component is inputting from the user or outputting to the user. This one also contains an 8-bit full adder made of 2 4-bit full adders and 2 exclusive OR gates. Exclusive OR gates allow me to flip the chip from addition to subtraction. Now let's talk about logic gates for a moment. Like I mentioned before, when you have a transistor, all it's really doing is a switch. But when you start combining those transistors, we can get some logic behaviors to appear. Now, I assume more of you know what logic mathematics is than the 5th graders did, but I'm still going to go over it. So logic mathematics is, instead of dealing with zeros, ones, twos, threes, whatever, it's dealing with mostly true and false values. And it usually functions pretty similar to how we intuit something. So for example, an AND operation in logic is comparing if one value and the other value are true, then your result is true. But if one value is true and the other is false, both aren't true, and so your result is false. Similarly, an OR operator would compare if one value or the other one is true, or both. And these are made of transistors. Almost all gates can be made of 2 transistors, arranged in different ways through these wires and some resistors for current limiting, so that when you put in, say, a 0 and a 0 to the OR gate, you're going to get a 0 out. But if you put in a 1 to either of those spots, you'll get a 1 out. And if you put in a 1 to both, you'll still get a 1 out. And here's something I want to clarify to everybody. I think this is very important for people to understand when using computers. When we use a computer, even something as simple as something that is adding 2 numbers together, that computer, there's no little guy in the computer looking at the 2 numbers, adding together and giving you the result. All we have done is found a way to manipulate that electricity through transistors such that when we put in the correct input, we get out the output we expect. This is a basic 1-bit full adder. It has 2 inputs and a carry input from the last digit, and it outputs the sum of those inputs and a carry sum, if there is one, to the next digit. This is the truth table for that, using zeros and ones instead of true and false. And like I said, this all operates in binary. So we can use logic to sort of simulate actual addition, because we can replace those trues and falses with the zeros and ones of binary. This is the truth table. So for example, if we're adding 0 plus 0 and carrying in 0, we're going to expect to get 0 out and nothing to carry. If we're bringing in a 1 and a 0 with a 1 carry, we're expecting to get a 0 sum or a 10 sum with 1 to carry. This is not doing addition, like how we would do addition. We have just found a way to put these transistors in the right order such that when we put a 1 and a 0 in, we get a 1 and a 0 out in the correct order. So let's talk about how I get data into the arithmetic logic units, and this is where the registries come in. The registries are these 2 sites on either side of the arithmetic logic unit in the middle, and they function as the most simple form of memory that this computer has. These take inputs from this main bus area and from the rest of the computer and store them until they're directed to output them. There's really nothing much else to this. This is 8 bits of memory. Now there's other memory on here with the random access memory, which I'll get to in a moment. But this memory works with something called an SR latch. SR latches are similar to what we've seen before in AND gates or half adders or full adders. But as we can see, the outputs are actually wired through a circuitous route back into their inputs. And the best way to describe what this is doing is when you input something to the store value, it sort of forms a loop inside of there. Now, the electricity isn't actually whizzing back and forth, but it sticks this in this one position until a value is sent to the reset, in which case it comes back to a 0 position. This type of memory is volatile, which means if you unplug power from it, it'll reset. And this is why we didn't use this form of memory in the past. We had hard drives, and now we have solid state drives, which function slightly differently than this, with large concentrations of electrons that will eventually degrade, but take 20 plus, 30 plus, 50 plus years to do so. But this memory is incredibly fast because you're not having to move physical electrons or move a magnetic disk with like a CD or etch grooves with an old record, and incredibly space and heat efficient, something that's very important in my computer. Now, the RAM is going to be the most complicated part of this build. RAM stands for random access memory, and it's basically a larger version of what I was talking about before with the registries. My RAM can store up to 256 different 8-bit values, and I can access those by putting in a memory address. This holds the individual instructions for the computer, sort of like the head of the computer. It consists of these RAM chips, which are these very small chips in this corner, and a lot of logic that converts both the signals from the computer into zeros and ones for the RAM, and the signals that the RAM holds into zeros and ones for the rest of the computer to understand. Now, this is also where programming this computer gets explained. The way I program this computer is I flip these little switches right here until it's at the correct spot in the memory I want it to be in. I flip these switches, unfortunately it got cut off in the photo, but these are 8 switches, until I have the correct data I want to put in. I flip this switch, I reset everything, I flip the switch back, and I do it over again. Now, to do that 256 times takes a while. It takes me about 1.5 to 3 hours, depending on the program, to put the program in here, and that's why this is running a simpler program, which is just subtraction. Because if I wanted to, say, have it compute squares, I would have had to spend 4 hours putting it in, and I didn't really have that time. That is also why I can't switch the function of it right now, because we don't really have 1.5 to 4 hours. In the future, when I donate this to Ryan, I'd like to change this so that you can write code on your computer and have this piped into the rest of the project. But I'll talk more about the future improvements I'm going to make and how I'm going to donate this in just a moment. We still have one part of this computer to talk about, and that's the computer clock. All of these parts that I've talked about need to be synchronized so that the instructions don't run before others. For example, taking something out of memory before it's been put into memory. And this is done using the computer clock. Now, this is not a clock like 12:48 a.m. This is a clock more like a metronome. That is a series of high and low, basically a square wave, high and low pulses at regular intervals, in my case 100 milliseconds, that is telling the computer you can execute the next instruction, execute the next instruction, next, and so on and so forth. I built this nice little clock module, and as you can see, it's not plugged in, and that's because it's not working. And there's a few reasons for this. When you make a clock module, that square wave has to be perfect. It needs to go perfectly to 5 volts in my case, and perfectly back down to 0. Now, if I were to plug that clock module in, on the surface, it would look fine. It would be a blinking light. That's all we want to see. But when I ran this through an oscilloscope, what I would actually see is that jump to the top would be fuzzy or bounce. It would jump to the top, come back down, go a little up, and then come. And this all happens in the span of maybe 1/10 of a millisecond. But that is too long for these other chips and other components to process. So they were executing commands twice. They were executing no commands per clock cycle. And what I ended up having to do is use this Arduino in the corner to provide a steady clock signal. Now, I have some stuff coming that's electrical shielding. So I believe the problem is that the components are too close together, and there's a small amount of electricity transfer between them, between the breadboard, which is inherently a little bit lossy. And that small thing isn't a problem with any of the other stuff, but because of the accuracy I need this component to have, it's messing me up. And so I've ordered some electricity shielding tape. Unfortunately, it's taking about a month to get here, so I wasn't able to get this done by the presentation, but this is something that I want to change in the future. And then this clock will be able to have 2 modes, both a variable mode where I can change the speed of the clock, so the computer can run up to a point faster and slower, as well as a step-through mode, which allows you to hit the button for each step, and that'll be helpful for Ryan in the future so we can show people what's going on. Now, we've talked about a lot about what it is, but let's talk about how for a brief moment. A lot of this presentation is what and not how, unfortunately, because the how is quite easy once you know the what. Building this project was actually fairly straightforward. The designing of this project was not straightforward. I designed this program in a program called Easy EDA. Easy EDA allows you to create schematics that you can then test by kind of simulating the flow of electricity through that virtual component. It's actually built for manufacturing custom circuit boards that you would order from a manufacturer, but I just didn't do that and use it as a simulation and then built it myself. The pros of this software for any of you wanting to use it, it's free. the cons of this software, it takes over 10 minutes for the simplest of tasks to be completed. Hidden keybinds, custom components I had to create, and just general user interface from 2003 made this process take many more hours than I was hoping. This ended up taking about 40 to 50 hours of my time to design. Process of building. This is my work area. This is my basement. It's not very organized. This is kind of how I function everywhere. I do know where everything is. I can point out what's going on here. But the workflow each day that I would come down after school or on a weekend was something like this. I would look at the schematic that I'd already designed. I would place each chip on the board and I would wire them up correctly. I'd plug it in and nothing would work. And then I undo all the wiring and I'd redo it and oh, this little thing was off and I'd plug it back in and nothing would work. And I would repeat this for a few hours until that component was functioning correctly. And then I'd do that again for the next component. Say I built the ALU and the registries. So I'd connect the ALU to the registries and nothing would work. And so I'd redesign something, or I'd reconnect these two parts, or I'd switch out the breadboard because this breadboard doesn't work. You get the idea. Finally, after about 20 to 30 hours of the build, we have this, which is a mostly functioning, minus the clock, computer. And as a quick note, I know these LEDs aren't lighting up. That is not a design flaw. Well, it's not really a design flaw. Most of these chips have internal 100 kilo ohm resistors that allow me to plug these LEDs straight into the ground without having to resist them. These chips don't. I bought them off of AliExpress. They might be ripoffs. They're cheaper than the other ones. But that just means I can't plug them right in and I don't have space to fit resistors in. So until I get some LEDs with internal resistors, those LEDs will burn out in about half a second and then I'm out of LEDs. So those aren't running right now. They also create a lot of heat when they run at that kind of high voltage, and that doesn't help with anything. So unfortunately, those lights aren't running. What you would see here, this would be counting up. This is what spot in the memory we're at. This would look seemingly random. This is because that's holding a number in hexadecimal, a 3-digit hexadecimal number, say CFF, that is describing what this next step is. And what that's really doing is saying, this light might correspond to the ALU, and it's saying, is the ALU inputting or outputting? If it's on, it's inputting. If it's off, it's outputting. And that's how all the data is stored in the back end of this. So that's how I would program it. I'd say, okay, this first step, I want the ALU to be outputting, I want the registries to be inputting, I want it to be in subtract mode, and so on and so forth. And then I put that program in, and I'd go to the next one, and so on and so forth. I'd like to thank Fred Anenstein. Fred Anenstein was my mentor. He used to be the science teacher here at our school. And after, my original mentor was going to be Mike Laskowski, who's on the board here. And unfortunately, he was not able to do this due to time constraints, but he did provide very helpful guidance on scale of the project and different sources for me to start learning more and understanding more about this project. So Fred Anenstein, I'm not a very good communicator, but we were able to meet a few times to get over roadblocks and to help him, for him to help me understand what was going on with the thing that I built and why it wasn't functioning. It happened a lot. I would also like to thank someone named Ben Eater. I have never met this man, but his YouTube videos explaining how RAM works and how computer logic works helped me through the design process tremendously. I would like to thank my parents for financing this operation and allowing me to absolutely blow up the basement with little wires everywhere that my dad kept stepping on. I'd like to thank Ms. McKinnon for coordinating the project and the presentation. I will be around, I think, over here after both presentations. If you have any other questions about building, designing, function, or just want me to go more in depth into stuff that I wasn't able to cover in this presentation, thank you very much. Just give me a second.
this is unfair. I got time to set mine up beforehand.
I did my project on skis. It came from a knowledge that I wanted to do something with wood, and combining that with my love of skiing, it seemed like a reasonable solution. A brief history on skiing to start us off. It began over 5,000 years ago in Scandinavia, Russia, and China, and was first used as transportation and hunting. It was incorporated into the military before becoming a recreational activity, and became a sport, per se, in the late 18th and early 19th centuries in Norway. Around this time, it also migrated to North America and Europe, and was first included in the Winter Olympics in 1924. Today, it includes multiple styles such as alpine, freestyle, and cross-country. It first came to Boulder in the 1940s in the form of a small area called Chautauqua Mesa Ski Area. This was built between 1947 and 1949 by the local community for the local community, and to begin with only had a few simple jumps, a few simple runs, and a tow rope powered by a truck engine. It hosted several small competitions, a few ski lessons, but was sadly closed in the early 1950s due to poor snowfall and not enough funding. It was temporarily attempted to be reopened in the 1960s, but failed, again due to funding and lack of weather, snow. But luckily, in 1962, we gained Eldor Mountain, which has been a very important ski destination for many Boulderites before highways and other such allowed for greater distance to be traveled in shorter time to get to bigger mountains such as A-Basin, Copper, or Loveland Ski Area. The difference between modern and old skis. I just do my skis as a modern shape, but original skis were made from a solid block of wood, normally hickory or ash, and were very heavy and unflexible. As skis evolved, they slowly gained something called ski shaping, which allows for the ski to bend in the places it's supposed to bend. As you can see on the side here, how it's layered, it is thicker in the middle and thinner on the sides, and this allows it to bend where it needs to bend, which is around here and here and not in the middle. It also has a shaping down the side, narrower in the center and a little wider at the tips. And this allowed you to have a tighter turning radius and a little bit more maneuverability, which older skis did not have. This is a fairly recent creation, coming around in the 1990s to early 2000s. And before this, we were stuck with really, really long and very straight skis. New skis are also made from different materials, such as fiberglass, reinforced plastics, epoxy, and sometimes even metal. And deciding not to do that was a fairly easy decision for me, as I had zero experience in any of the field, and I didn't really want to mess around with more or less dangerous materials. So I made mine out of layered wood. The process started with finding a mentor, as I knew I wanted to do something with wood. For this, I decided to look local, and thankfully our very own woodworking teacher, Mr. Felkley, sitting over the back, agreed to help me. He has been a very important part of my building process. After finding a mentor, I rotated through the several ideas that I had, and those were skis, a catio, or a cat tree. A catio is we have two cats and we torture them by leaving them inside. This is because we live on the front range, and larger cats that like to roam around these areas would very much enjoy to eat our cats. And so as much as they hate it, we keep them inside. We do have limited access to the outside world with them, and this is via a catio, but I was considering building them a bigger one, giving them a little bit more freedom. The The other option was a cat tree, and this is because we spend most of our time carrying around our cats and being their cat trees for them, so might as well build in another cat tree in hopes that they don't do this as much. I ended up deciding on a ski, one obviously because I love skiing, but another is I was told by other people that these were not exciting enough projects. So the skis ended up being what I chose. The very first step was deciding what wood I wanted to pick, and I chose poplar due to its prevalence in modern skis, its flexibility, and its contrast against the other wood, which was cherry, which I picked for its natural grain, color, and it is one of my favorite woods. This ski, you can clearly see the grain is very pronounced. The next step after picking up what wood, I ordered that. A small hiccup for me was I didn't realize it was coming from Buffalo, New York, I believe. And this caused me to procrastinate slightly on ordering the wood, delaying my whole project later than I would have liked. I ended up getting the wood, but it arrived in very, very long rolled up strips. And so cutting them down using a bandsaw, I was able to get to the proper length and width that I would need for the rest of the project. Next was to decide what to make the mold out of. I ended up going with pink XPS foam due to its ease of cutting on a bandsaw and its ability to maintain shape under pressure. Making the mold, used a bandsaw, roughly drew out the same shape as a pair of skis that I have, which are Ben's Chetler 100s, and that's how I got the correct curve for both sides. And then layered cork on top to limit any inconsistencies that came from a bandsaw, as I found out I'm not very good at cutting straight lines with a bandsaw on foam. After that was on to gluing and something that not a lot of you are probably familiar with, which is a vacuum bag. This is used to make wood veneer and curved wood pieces, and allows for an even application of pressure across the whole wood piece, and is a very big help in making bent wood, as it eliminates the need for inconsistencies that come with clamping down it, running into problems where, oh no, it's sliding off here. It just keeps it nice in the bag. So I glued it using a 2-part epoxy and a paint roller on both sides, and for that I had the help of Mr. Buckley. And after properly aligning it on the mold, I slid it into the bag, and each ski had to be done independently and overnight to harden and sit. After taking it out of the bag, next step was shaping, and for this I used a bandsaw, which has been a huge help the entire project. It was needed for the foam, the original cutting of the wood, and the last part of cutting it out. After cutting out the ski shape on the bandsaw, one of the final steps was to even out any inconsistencies that came from my lack of cutting skill on a bandsaw using a sander and a hand plane. The art was something I had thought about the whole time I was making the ski, and it was a difficult decision as it is a key part in brand recognition and ski identity for most companies that have skis. And I ended up deciding to wood burn it due to its ability to kind of blend in with the wood without entirely disappearing. I chose to do an elk as it is a very popular animal in the US or in Colorado. Trees, because we have a lot of pine trees here, and a waterfall at the bottom because I needed to fill up a little bit more space. The next step was to coat it with finish, and I was practically done. Although these skis don't have edges or a PTEX bottom, which modern skis do, I have been in consideration of adding it ever since I began. I have the ability and the parts to add PTEX and edges, but I'm still at a loss for, I don't really know, I don't really want to, because I don't want to take away from the pure wood of it, but I also would like to add it to make it a little bit more of a finished ski. Before I go, I just want to quickly say something about the snowpack. Colorado snowpack has been steadily decreasing in the past few years. It's been seen a very, very sudden spike in decrease. It is caused by warmer temperatures and very inconsistent snowfall. Many of our snowfalls have come in the form of rain, which is not very helpful. And if this weather keeps up, we will not only lose all of our skiing, which I would be very sad about, but it also affects the lower region of the United States, as it will drive the Colorado River, lose a bunch of water to California, dry up the desert, and cause a lot of people to lose fresh water. Ending on that happy note, I'd like to make a special thanks to all the people that have helped me. My mother for funding my project, Mr. Felkley for being the best mentor I could have ever asked for, Manisha Bono and Molly McKinnon for organizing and keeping the project somewhat on time, and many others for being curious and being helpful when needed. That is about all. Thank you.
Like this, one of the reasons I didn't build it like this is because it was going to cost about $2 grand. This whole thing ended up costing about $175, and most of that cost is in the breadboards. Breadboards get really, really expensive in order to ensure that they actually work, unfortunately. So it's about $4 to $8 a breadboard, and I needed 15 of them.
Before, I'm just gonna make this easier for some who may be limited time. Feel free to stand up and come speak to us
That is
instead
not
of
the
treating
deal.
like
Feel not free.
Feel free to do this.
Feel free to ask Eli a
It'll
question.
be a little bit more time efficient, shall we say, since it's taking a while to do this panel format.
Alright, we're gonna drag this out now. Forever.
Why did you choose to make a twin tip ski where it curves up on both sides as opposed to just like where it's flat on the end?
I thought it looked cooler.
That's fair.
Eli, are you planning to put bindings on your skis?
I am not planning on putting bindings.
So they will be more
There'll be wall decoration.
decorative. Got it.
My question for you, Solomon, is what are you planning to study then? Computer science, I'm guessing?
I'm going to go to school of mines for electrical engineering. I just made that decision last night. The decision has been like a year in the making, but I just
Yeah, that's.
My other question to you was, while you were doing this project, science comes from nature. Did you have an opportunity or time to look at the human brain? Because that's chemistry, right? That's what you do.
I have, not through necessarily this project, but just through liking computers and liking computers since 5th grade. I find it fascinating that so often when we find the most efficient solution to something, it's already been done millions of years ago by a tree.
Yes.
My favorite example is solar panels. The most efficient way to put like the conductivity that pulls the electricity in is the pattern of veins on the backside of the leaf. It's the exact same all the time. And so there wasn't as much through this. This was a very kind of technological process, but through other things, I do think that, and it's something I'd like to keep.
Because when you spoke about transmitters, that's how our synapse in the brain
Right.
works, yeah. So
Right,
it
and-
was nice to, when you were talking to, for anyone to have that alongside. So I think you did fantastic.
And
Eli, was it intentional to only do the design on one ski?
Yes, it was. I originally was gonna do it on both. However, I decided to leave this one untouched because I really did not want to put anything on this piece of wood. I thought it looked really, really pretty by itself. And I have half of an elk head on one
Show
because
us.
that was the original plan.
Hard
But
to see with
after
like the.
doing this one, I couldn't get myself to do it.
Yeah. Sorry. I'll come check it out.
Yes.
Why did you have to order the wood from Buffalo, New York?
I am not quite sure on that, but that was under the recommendation of Mr. Felkley, as he knows a lot about wood and this is wood veneer. I took his expert opinion on that and decided to order.
Is it known especially?
So,
Upstate New York?
a lot of hardwoods are prevalent back east, and there's a company called Certainly Wood that just deals in really thin veneer woods, and they have a great selection. They ship quickly, and I've worked with them quite a bit, so it was just familiar. And just to say too, one reason why Eli's skis are not usable is partially my fault. Never having built skis before, we were kind of winging this. And knowing how Eli probably skis, I didn't feel comfortable having him flying off a mountain on skis that I was partially responsible.
100%.
George.
Got another one for Eli. How does the flex on your wooden skis compare to the flex on, say, the skis you actually ski on? Or
Creepily similar. I was not expecting the same to be the case, but it is.
Wow.
I don't want to snap them obviously, but it was kind of creepily similar, and so I could very easily have made these into a fully functioning working pair of skis. Yeah. Yes, Phineas.
Also for Eli, how many layers of wood are in the skis?
Depends on where in the ski you're talking.
The thickest part.
Thickest part, I believe it is 8. They start blending together when there's the 2 types of wood very close together. Excellent, thank you.
Solid account.
Okay, there we go. I give everyone 5 seconds. There's no more questions.
I was expecting to see some of the calculations, some demo of.
Which part? It was running. So the computer is painfully not powerful. It pained me when I designed the whole thing to realize what it was capable of doing. But again, I can't change the program because that would take between 1 and 3 hours of me sitting there flipping switches. I don't think you guys want to watch that. I can plug it back in again if it still works for moving over. But it's just something to think about really, is that something this size, and most of this is at human scale, is so incredibly simple. And so something like this, which has so many more transistors in such a small area, is just incredible. That we're able to build this and that we're able to buy this for less than, $8 trillion. Yeah.
I would actually love to watch you do that for 1 to 3 hours.
Hi, this is my brother. He is welcome to do that when he's supposed to be at work. I think that's a good time for me to do that.
One more quick question.
Yes.
I'm curious, Eli, what your plans are after graduating. If you're going to.
I am going to, in form of engineering at CU. It originally was electrical, but due to me not really trusting myself with electrical, it has shifted and it's undecided, but I know I want to do some sort of engineering. Some form, not sort.
Question for
Close us out.
So you mentioned you're planning on making it so you can program it on your computer. How are you planning on actually doing that?
So I'm going to use these little things, which is a 28C64. This is both a electronically erasable programmable reader-only memory and a very simple CMOS computer, which is just a very simple type of computer. And this allows me to write the hexadecimal numbers, into a serial display and run it through the Arduino, and then that'll program it onto this, which will disseminate it onto that. Now, the reason I didn't want to do that is because this thing is painfully insignificant enough as is. This is more powerful than that entire thing, and unfortunately, it's the only thing I can really use in this scenario. But I didn't want to include it in the end thing because it draws even more attention away from the actual thing that I built by being incredibly hand machined in China. So that's why.
I have a question for both of you. Do you have any advice for juniors that are going to be stepping into this role, that are going to be finding their own projects for next year?
Yeah, get yourself a mentor as quickly as possible. And that's not to, don't just like grab some dude off the street, you know what I mean? But having a mentor, preferably by like midsummer, is really, really important. Having someone who understands the level of project you're doing. I went through, obviously, kind of a couple mentors, and so I didn't have a steady mentor until maybe November, and that hurt me a little bit in terms of time, and then I had to spend a lot of time in January doing more than I would have liked to. I would have liked to have been farther along at that point, and part of that was because I didn't have someone to go ask questions and stuff that was just kind of available 20 sometimes 7 on call to ask those questions.
I also have one. Make sure you and the people who have helped organize the senior project know all of the timeline of the senior project. And don't underestimate the amount of time that it will take.
You said took you like 40 hours just to do the
40 hours
design.
of just the design, and part of that's the program's fault. And if I had paid another, like, I think it's $250 for a better program, I wasn't gonna do that. So, you know, I paid $250 worth of my time, if you calculated it with minimum wage, to work with software that, you know, looks like my terminal. Henry, let's close out.
How long did it take you to like? How many hours did it take to fully make this?
No idea.
A lot.
Guys, thank you so much.